So there's kind of a spoiler in the title here that would imply that it does scale, but we'll maybe get to that. So the talk's called The Road to 2 Million WebSocket Connections with Phoenix. It's based on a blog post. Has anyone read the blog post? Can I get a show of hands? Has anyone read the blog post in the last week? Okay, good, everyone can stay. Oh wait, that one guy, you go. So it's called The Road to 2 Million WebSocket Connections with Phoenix. I originally called it Benchmarking Phoenix Channels. But I was told it doesn't get the sort of impression on Hacker News that we wanted. So it sits nicely between that and 2 million reasons why you need Phoenix in your life. So this is me, and this is how I choose to represent myself on the internet. That's like a Jenga tower in my mouth. I'm Gazler on the internet, except from Twitter where I was late to the party. So I'm the Gazler. And I work at a company called VoiceLayer. I'm doing push-to-talk stuff. So, format of the talk, I'm going to start with why we're doing this. Then I'm going to go how we're doing this, which there's like 5 slides of XML, but it does end. Yeah, that guy loves it. And then we'll go on to the results and then talk about what's coming up in the future, maybe, probably. So why do this? If you've seen any Elixir or Phoenix presentation, you've probably seen this WhatsApp blog post mentioned, which is 1 million or so 2011. And it's kind of a talk about how in 2011, WhatsApp were able to get 1 million connections on a single machine. And then they were able to subsequently get 2 million at a later date. And that's great, and it kind of is a testament to how the Erlang VM works. But it doesn't really say much for Phoenix. I mean, it shows us that it's technically possible, but there was no real proof of it. There was plenty for HTTP. So there's like the Phoenix Showdown. Chris wrote a blog post. And there's also the framework benchmarks that come out that you should totally ignore because they've done it wrong and the results are bad. But there was nothing for like persistent connections. So we needed some measurements for it, really. So what makes benchmarking WebSockets different? Why don't you just like fire up Apache Bench and do your thing? Because Apache Bench, don't use that, use Work. But even if you're using Work, it's different. So it's a different protocol, using the WebSocket protocol. So the connections have to stay open, right? You can't just like, if you use Work, then you can open a connection and then it'll close and give you the response and the amount of bytes that were transmitted. And then you can go again. You got to hold on to the connections. And that kind of results in an increased memory usage. And then there's this weird like hard connection. So there's like a port limit of about 65K and then 1,000 are reserved. So it's 64,000. And you can increase this. So if you imagine you've got like the client IP and the client port, and then the server IP and the server port, and that needs to be unique. So that's why it's 64K on one machine, because you've got the same client IP and port, but on the server, we don't have the same problem because all the incoming connections are different. And yeah, so you can fix that by if you add additional virtual IP addresses, but in this particular set of tests, we didn't have that option, so we didn't. So memory usage was our main other one. So the application we're benchmarking, or we did benchmark rather, was the chat application that Chris put together that showed you how chat worked. And there's a link there if you want to go and look at it. It's quite old now, but we had to upgrade it recently. There was one difference, so I don't know if you can read that okay. But basically there's a timer send after that would ping, a timer send interval rather, that would ping every 5 seconds. So this is like when you're on the chat application, you'll see a ping come in from the server every so often to let you know that a message has come in and to let you know you're still active. And whenever anyone joins, so this is like an after join that gets handled, it sends a message to everyone to say that hey, I've joined the channel. But we don't want that in this case because if you imagine you've got an arrival rate of like 1,000, you've got 10,000 existing connected users. And Keith showed a great slide yesterday which had like all these messages coming in and then all the messages coming out. And I'm not as good as animations, Keith, but I have like an artist's impression of what that may look like if we'd left it on. And it's something like this. So yeah, so we turn that off, and here's what it looks like if you don't. If you're looking at like the web application, you just get this constant stream of incoming users that all say foo. So yeah, so turn that off. So the way we benchmark this is we used an application called Tsung, which is an open source multi-protocol distributed load testing tool, which I took that straight from the website, so it's a good description. It's written in Erlang, so that's good if you want to look in the code, you can see how it works. And it started development in 2001 under the name IDX Tsunami. Since version 1.5, it actually supports WebSockets, so that was good because that was what we needed, and that's one of the limitations with some other tools. It supports multiple machines as well, so you don't just have like this one machine that you can use to go off and do requests. So you got that, and it also produces nice charts, and it's got a web dashboard that you can use, which is really helpful. You can look at it once you're running the test and see what's going on. So here we get to the XML. So it's configured using XML. You have simply one XML file, and it's got several sections. Again, can't quite, maybe I can, is that better? Yeah, so you got clients, you got servers, you got load, and you got sessions. And one of the machines will have this config, and we call that the controller. And all the other machines that you use to run the tests are clients, and the controller powers them. So the client's configuration, you've got these little blocks with a client and a host name. So in Tsung, everything is configured with a host name. So that's why you'll see like Phoenix 1, Phoenix 2, and it can go up all the way to wherever you want, depending on how many clients you've got. You can allocate a weight as well. So in this example, the middle one has got a weight of 2, and the other two have got a weight of 1. So that means that 50% of the time, machine 2 is going to get hit, and the other 25% for each other machine. You've got max users as well. And you want to keep that below your machine limit, be it the port limit or the memory. Otherwise, bad things happen and it'll probably crash. So make sure you keep that below. So if you've got 60K, keep it 60K. You'll find out after you first run it if it's too high because it'll crash. So you can also have multiple virtual IP addresses, I mentioned earlier. You can just specify them inside the client block. But we didn't do it in this case because Rackspace set up the machine for us. And we didn't have access to like the network adapters to add additional ones. And you can also, there's this flag to use controller VM. Make sure you set that to false, otherwise you're sharing a VM with the controller. And you don't do that, especially if you're distributed across multiple machines. So the server is also configured in a similar way. You can specify the server block, and you've got, again, a host, so it uses host files for that. Or you can put in an IP address here as well, actually. If you've just got the IP address of it. The port and the type, so there are different types you can use. You can use TCP, HTTP, WebSocket, and so on. We actually use TCP, and I was making these slides, and I was like, why do we use TCP if WebSocket's available? And I was getting these insane results when I tested it with WebSocket. I was getting like 8 million concurrents, and it was insane because it wasn't holding onto the connections. So we use TCP, but I haven't really investigated why that was the case yet. And again, you can do weightings here as well. So the first machine's got a weight of 4 and the second's got a weight of 1, so it'll be like an 80-20 split. Load is how you get users and connections opened to your server. So it's phased, and you can say, you know, I want one phase of like 10,000 users and want another phase where another 5,000 join. So you can simulate different levels of load. They have a duration as well, so a phase will last a certain period of time. The total duration can be like just under 50 days, so I have no idea why you want to run this for 50 days, but that's sort of the upper cap. And you can loop over them as well. If you want to run like the 10,000 one twice and then the 5,000 one once, you can certainly do that as well. And the way we did this is we just set the duration really high and manually terminated. So when it got to like, it would even off and we'd have, you know, we'd just kill it then because we had no idea of what we could really handle. So we didn't know what to set this to. And the arrival rate is just the number of incoming connections per time period. So you'll see here, I've set it to 1,000 per second, so that's how that works. And then you've got sessions, which is probably the most interesting one. So sessions are how the connections interact with the application. So in our example, we open a connection on the WebSocket, then we send a join message to join the lobby, and then we just wait forever or for a long period of time. Again, for the same reason, because we had no idea what numbers we were really looking for. So we just so we opened the connection and then we just waited until we killed it. You can use Erlang terms in here as well. So you can do this like weird double percentage syntax and then call a function. So we use here TS user server get unique ID. And if you remember the example I showed earlier, you see that each user had a number when it was scrolling through. and those numbers were generated using this piece of code, so it's just like a sequential identifier. And you can have different request types as well, so these are the WebSocket ones, but if you're doing HTTP, then you'd set that to HTTP, and so on, and you can specify the path. And you can also have different probabilities per session, so this is pretty interesting, where you can say, like, this has got a 100% probability of being executed, but you can also say, like, well, 20% of my users I want to both join and then send a message as well. So we didn't do it in this case again, but this is how you could simulate like a chat room where some of your users are sending messages, but most of them are just sat there waiting. It has this like web interface, so you can see here, this is the status page, which is cool. It's show you like the number of running users, connected users, the request rate as well. And what's interesting about the request rate is that you set it to say 1,000, but because you're generating this load and you're probably generating from different machines, you can't really regulate it. So it's like as close to 1,000 as it can do based on how it's been performing. And then you get the number of active nodes and the current phase as well. So if you're using 5 Tsung clients, then the active nodes will be 5. And then you got these as well. These are the charts that are generated that you may have seen periodically. We don't actually show many of these. The only one I think we do show is the bottom left, which says network traffic. But you can look at all the different metrics here that it gathers based on your connections. Throughput's quite an interesting one as well. The one that you'll see the most is the brag one. So there's 2 lines here. There's the one on the top and the one on the bottom. Yeah. And the reason I have to specify this is because I would love to go by color and say there's the green line and the blue line, which is technically true, but they swap. So the top one is always the number of users that have been generated, and the bottom one is always the number that have connected. So in this case, you see they go up pretty evenly, which is good. That's not always the case. So so that's all the XML done, by the way. That's gone. There'll be no more of that. When we first went to run this, this is the command you use, Tsung-f config, your config file, and then start. So when we came here with one server, which had like 15 gigs of RAM and 4 cores, and Rackspace kindly gave us 3 of these to play with. So we used 2 of them as clients and 1 of them as server. And if you're struggling to imagine what that looks like, it probably looks like this. So, so we're at this point we were pretty hyped. You know, we're like, okay, let's do this thing. Let's run. Let's see what we can generate. Let's do some load. You know, if WhatsApp can get like 2 million connections, we can probably get like loads maybe. And then this happened, and so again, as I mentioned, the line on the top is the number of users that have been generated, and the line at the bottom that's capped at 1,000 is like the number of connected, and that's not good because 1,000 is less than 2 million. So what's going on here? Like, you know, we're like, well, this sucks. We should stop now. There's this number that you need to specify. It's called the U limit, and it was alluded to earlier. And it's the number of open file descriptors, right? And what you want to do with this number is you want to set it to something that's like super high that you're never going to reach, and then that way, when you run it, like it doesn't matter. So we did that and set it to 2 million. And you want to make sure this is set as well every time you restart the server. So sometimes we'd run a test, and then we'd go like, we should probably turn it off and on again to clear the state. And then we'd run the test, and we'd see that 1K again, and be like, the U limit, we need to start again. And it takes a while to do these things as well, so it's quite frustrating. Anyway, so we ran it after this, and we got this more pleasing result. I mean, it's not amazing, but you'll see here, what's good is the lines go up pretty uniformly, and like come up as 1. And you'll see here the blue line's on top, whereas previously it was the green one. And it gets up to like just under 30K, and then there's this drop. But the good thing about this drop is that both lines drop together, and that means that Tsung has dropped the connections and not our server. Sometimes you'll see they split, and that means that we've dropped them. So we were at like 30K, and that's fine, but it's not the sort of level we were expecting. And at the time, Chris, Jose, and I were on Skype, and like after 10 minutes, she was like, hey, I got an idea, try this branch. So he'd done this optimization. And the commit message here says, only rely on ETS tables inside local 5 months ago, Jose William. It's not 5 months ago now, but it's 5 months when I did it. And you'll see here what's interesting is there's one change, and there's like 14 insertions and 69 deletions. And so there's been way more code deleted than inserted. And what this commit did is before we were tracking like a hash dict of the subscriptions, and we had an ETS table for the topics. And we just ditched the hash dict and just like managed everything inside this one ets table, which is Erlang term storage. So we've now just got this one place where everything's stored. And that was pretty good. It got us like twice the performance. And you'll see here when I was talking about the split, there's like a split just here because I don't have a pointer, but it's there. And that's when it starts like dropping connections. And it drops them in such a way that it like drops it for a long time, and then for some reason it creeps back up. So it recovers, but then there's again a massive spike down where they're not terminated. So it's a good improvement. It's like a 2 times improvement, but it's not, again, not near the level we were looking at. And that's when this came in. So Observer is a tool that ships with OTP, and you'll definitely have it, and you should definitely use it. You can open it with observer.start, and what's really good about it is you can open it remotely. So you don't need to like do this on the machine you're running on. And the way we found this is we had this server that was running the Phoenix application, and we would open a node locally, node.connect to it, and then observer.start locally. And we saw this, and we've ordered it by message queue size here. And you'll see there's a timer server, and the message queue size is high, and it never goes down to 0. And as more connections come in, the number keeps getting higher and higher. And that was another bottleneck, I guess, that we found thanks to Observer. So you've got this tool here that is really useful for finding it. So in came this next optimization. There's actually 2 commits, but I've squashed into 1 for convenience. And it says remove unneeded heartbeat since Cowboy handles timeouts. But the first thing we did was we were using timer.sendAfter, and timer.sendAfter maintains like a central timer server for your processes that register, and it's a really expensive operation. So if you need to do something after a period of time, you can either use it in like your gen server, you can specify a timeout at the end, or you can use process.sendAfter. I actually don't think there's any use case that I know of that you should use timer.sendAfter for. If anyone has one, then tell me. But then we found out after doing this change that Cowboy actually maintains a heartbeat anyway. So what we were doing is every 30 seconds we were sending a message to the client saying, "You're still alive?" And it said, "Yes, I'm still alive." And Cowboy handled that for us anyway. So you see here, again, 5 insertions, 38 deletions, just delete code and things get better. So there's a lesson that you should definitely learn. And it looked more like this. So this is a cool chart. It goes up to, so Tsung generates the 120,000 users, and then it goes down a bit. But you'll see, again, there's this clear split around the 40K mark. We ran this test for ages as well. This was running for like 12 minutes maybe. And then, so it goes up and it's great, but there's still at some point like 40,000, a difference between 40,000 between the number of generated and the number of connected. But this was the most load we could generate with our 2 machines. And you'll see right at the end of the line here, there's like, it just goes from 100,000 to 0. And if you want to replicate this, just kill the server when you've got 100,000 connected connections, and it'll just do that, and it just kills them all immediately. So we need more machines, right? At this point, we're capped with what we can generate. So at this point, Rackspace kindly donated us this amazing machine. It had 128 gigs of RAM and 40 cores, which is a lot. And we had these like the 3 clients that they'd already given us, and then we set up some of our own machines as well. That have 4 gigs of RAM and 4 cores, which we found was about enough memory to handle 60,000 connections. And as I mentioned earlier, because we couldn't do networking with the machines we already had with virtual interfaces, we decided to just set up a machine for each 60,000 connections. So this is what HTOP looks like on a machine with 40 cores. It's pretty cool. So I think it's 20 cores with hyperthreading, and it's probably worth noting I actually set one of these machines up myself, and hyperthreading is disabled by default. And you go into HTOP and it shows 20 and you get really disappointed. And it should do 40, so you can enable a kernel flag. So if you try this yourself and you only get 20, that's why, and you can change that. And again, you're probably struggling to visualize it. So this giant machine here is obviously the big one. Anyway, so we ran it with this. So if you imagine we've got these 8 machines, 60,000 connections each, we can generate about 400,000, maybe just over. So this is like a dolphin chart. It's sort of shaped like a dolphin. And you'll see that at like 50,000, again, there's a split. And at the peak here, so we get like 330,000 connected users, which is a big number. but there's like 100,000 dropped connections, which just is not good enough. And we were quite disappointed by like the number of disconnects. You know, it's great having a high number to tweet about and to boast about, but we didn't really. When we were tweeting about this, we weren't like, "Hey, we got 300,000 connected and 100,000 that didn't connect." Yeah. So we need to fix that. And we thought, well, what if we swap it over, right? What if it's maybe a hardware limit? Maybe we'll take the big machine and we'll put that as the server, and then we'll use one of the clients. And we did that, and we thought, right, let's see what the big machine can do. This is like 40 cores and stuff, and the way I'm hyping it is probably going to set up the disappointment, because it looked like this. So on the left, we've got the machine that we're running on, and on the right, we've got like the big machine, and they're exactly the same. There's like a 10K difference, and you're thinking, well, it's like a 10 times more powerful machine, so obviously we'd only do 10,000 more connections. And you know, I'd love to end here, but there's more. So what was causing this to happen? Like this was good in a way, right? Because it's disappointing, but it also shows us that it's not a hardware limit. The problem's in the code, so it can probably be fixed. And indeed it can. So this is the third optimization, and there's a couple things that are striking about this for me. There's probably only one that's striking for you. But the commit message says change PG2 ets from bag to duplicate bag to improve performance for elements with same key 5 months ago, Gabby Zuniga. And the reason that's interesting for me is because Gabby's actually my colleague at VoiceLayer. He's the CTO, and I had no idea who was doing this. And I came in one morning and like I opened up GitHub issues and I saw this pull request from him. So I was like, hey, Gabby, I didn't know you were doing this. You could have said, but he didn't. But the more interesting thing is that there's one insertion and one deletion. So like, it's probably going to be more interesting after the next slide, actually, so I'll show that. So this is the difference that one line of code can make. Yeah, it's kind of a big deal. So what you'll see in the right one is like the two lines just go up uniformly up until like maybe the late 200,000s. And then there's like a peak off. But the other great thing here is that eventually, like the lines meet. Like there's maybe a handful of dropped connections, maybe like tens of dropped connections. But at this point, again, we'd maxed out our machine. But I just want to go over this optimization so you can see what the thing was. I've put the diff here so that you can read it. If you can't read it at the back here, the difference is the word bag has been replaced with the word duplicate bag. So what does this do? So you should know your ets types because they're important, and you saw that from the last slide. So what's happening is with a bag, whenever you insert an element into the table, it'll do a check to see if the key already exists, and if it does, then it'll reject it. I think maybe it overwrites it. It does one of the two things. But the duplicates don't matter in this case because each subscriber is unique. So what was happening is you're inserting your element, and as it grew, and this is where the bottlenecks were earlier on, as it grew, the number of elements it would have to check to see if it's a duplicate would increase, and that's why it was capping at, like at 50K was where the problem started. If I just go back here, like that's when it started to split, so that's probably when it was starting to hit the limit, and it just got worse and worse from there. But each subscriber is definitely unique, so duplicate bag's fine. But the main benefit from this, beyond the bigger number, is that the arrival rate we were able to increase that from 1,000 to 10,000, which you can imagine dramatically reduces the amount of time that the subsequent tests take. So we were capped on machines at this point, and Justin, I don't know if he's about somewhere, but his company, Live Help Now, actually set up like 40 servers for us, which was pretty generous because it allowed us to do more numbers. So we ran it with all this load, like all these machines that we had. And you'll see that this slide here, it goes over 1 million. It goes to like 1.1. So this was like the first point where like, yes, web scale, like 1 million. And then we remembered that that's a 2011 thing. So, so we were like, 5 years behind. But you'll see here, there's like a very obvious problem at the 1.1 million mark. So it keeps going on to like 1.5 million, right? But at this point, so the last time you remember the problem was 100,000 users didn't connect. And this time we've got like 500,000 users not connecting. It's that's a lot of dropped connections. I mean, being able to get up to 1 million without any dropouts is fantastic. But you can probably always do better. So at this point, we were thinking, well, all the low-hanging fruit's gone, right? But we did say that the first time, the second time, and the third time. So there's maybe still low-hanging fruit, existing if you want to try and find it. But what would occasionally happen is, so you've got all these, 40 machines or 45 machines all connected to this one server, and one of them would crash, and its 60,000 connections would all drop at once. So you get 60,000 down messages on the server, which is what causes timeouts on new connections, because it's still handling all these down messages. And the other issue is like a broadcast was taking 5 seconds to all users, and Justin sounded really disappointed when he found that out. He's like, yeah, that's 5 seconds is like 3 seconds too long. So what we did is we parallelized the broadcasts, which fixed the broadcast time, but we still had the issues with the timeouts when one of the nodes would die. And that kind of leads us on to this optimization, which says add random local pool and sharded subscribers, Chris McCord. So Chris wrote this. I think it was maybe Justin's original idea, and then Chris implemented it. And it's 73 insertions and 51 deletions, which, so disappointingly, we actually had to add code in this case to improve it. And this was the first time we added code, so yeah. So what we did in this case is we, instead of having like this one process handling all the connections, we have a pool of servers and a pool of ETS tables. And then based on the PID of the subscriber, you can use this function Erlang phash2 to get a consistent result back from a shard size. So if we had like 45 shards, we can say that for this PID, it's always going to go to number 3. So that's the function that we use there. And you can configure this with the pub/sub pool size, and you want to set that to the number of schedulers. You don't need to do this manually anymore, because when I went to do some additional tests for this, I was like complaining to Chris, like, Chris, the results aren't as good as last time. He's like, yeah, what's your pool size set to? I was like, yeah, I definitely remembered to configure that, because it was set to 1. So, so that's not high enough. So you can set, but like I say, it defaults now to the number of schedulers that the Erlang has available. But with this, we were able to get like 1 to 2 second broadcasts, which was much better. I'm just going to go over this commit in a little more detail. I actually took these slides straight from Chris's Erlang Factory keynote, so if you recognize them, that's where they're from. Thanks, Chris. So it's, this is the old version, so each node has a pub local, an ETS table, and a PG2 server, or gen server, and the connections, the communications are done via the PG2, and then locally there's just the one. And afterwards it looks like this, so you've got n number of local servers and ETS tables, so you've got much less going to a single process, and then PG2 still being used for the connections. And Sasha mentioned in his talk yesterday that, about using an atom for naming, and that's what we do in this case. This was the case he mentioned about Phoenix pub/sub, so we know that it's not going to exceed the number of schedulers, unless you set it to a ridiculously high number, which you shouldn't. And with this, so this is, Chris showed this earlier, this is the 2 million one that everyone likes to tweet about, and you'll see that the line goes up. It's a pretty wavy line. You'd expect if you set the arrival rate to something uniform, that it would go up linearly, but it doesn't, because it can't. You've got like 45 machines to try and get a uniform connection stream coming from, and you just can't. So that's why it's like a really wavy line. And then you'll see it seems to cap out at exactly 2 million, which I don't know if you remember why. We'll maybe go into that. So that's what, but it keeps generating users. And we actually, I need to confess that we actually never got to 2 million. We got to 1999984. But the good news is here, the 16 probably aren't dropped connections. They're probably the file descriptors being used for other stuff on the machine. So, so there's a positive. But the really interesting thing here is we're not even memory maxed. We're using 83 out of the 128 gigs. So there's probably a bit more that could be done with this. But you see all the cores are idle, and they generally are unless a message comes in, and then they'll all spike up and then they'll come back down again. So so I'm just going to go over the ways you can optimize. So the first way is like say after like 10 minutes, she was like, hey, use this branch, it's better. And that's one of the ways. So I guess not many of us can do that, but someone probably can. The second way is to use, so you've got all these amazing tools that ship with OTP that you can use and they're available, and you should learn how to use them so that you can find these bottlenecks. And I would encourage you to do these sorts of things on your own machines as well, because just because Phoenix can get 2 million, that says absolutely nothing about your actual, what you've built. All we know is that's what the framework's capable of. Isolate the bottlenecks as well, so this is an interesting one. When I spoke to Gabby, I was like, Gabby, how did you find the duplicate bag thing? And he said, well, I just sort of had a theory on where the bottleneck would be, and I just ran it in isolation. I was like, yeah, I never thought to do that. I thought you'd have to run like all the things at once and do like these massive distributed tests, but you don't. You can find things on your like laptop, just if you know where to look. Know your data types. So I don't think I'm going to be making the duplicate bag issue again. I think every time I'm creating an ETS table now, I'm going to really consider the type that I'm using. And use a pool if a process is bottlenecked as well. So like this is one of the first things you should do if you've got a single process that's taking all this load. You should probably consider using a pool. Lots of libraries, Ecto, well, DB Connection, for example, do the same sort of thing. So at this point, we've got like essentially a chat room with 2 million people. And I can't think when you'd ever need a chat room with 2 million people. But just for reference, like 2 million would be enough to host the population of Phoenix in Arizona in a single chat room. So it's a lot. But I mean, practically you probably wouldn't have a chat room, but you may have some other use case where you need all the machines to be able to talk to each other. But do they do anything? The answer is yes. So you'll see that this is the network traffic chart. And you'll see all these little spikes, and that's where like Chris and I were testing it, sending little messages to each other like hello. And you see this massive spike at the end, and that's when Jose decided to give it a little test as well and post the entire contents of a Wikipedia article to 2 million people. I don't know which Wikipedia page he chose to post, but if I had to guess, I would probably say this one. Okay, so if you haven't worked out yet why the chart looks like this, Chris did mention earlier that the configuration was wrong, and this was the culprit. So when you set it to a number that you think you're never going to reach, probably double it, because we thought, let's set the U limit to 2 million. That's a high number, and it's like if we didn't, we had all these machines. And we got this result, but we couldn't do any more. We had to shut them down at some point. Justin's company was paying for them all. So we actually didn't get to max out the machine, which is unfortunate, but maybe at some point in the future we will. So some common issues you'll probably run into if you want to run these yourself. Everything requires a host name with Tsung, and it needs to be correct as well. So when you're setting this up, set up your etc host file with all the IP addresses for all the clients. And the clients also need the controller in the host file. So make sure you do that. It needs to be correct for every client as well. It seems like a weird thing to state in a slide, but make sure it's correct. The SSH keys need to be set up as well. So the controller needs to be able to communicate with all the clients. And you do this via like your authorized keys. So make sure that you can SSH to all the clients from the controller. And the U limit needs to be set. So U limits give us a lot of problems on the server, but this also needs to be set for both your controller and all the clients. And just every machine you use, just make sure you set the U limit. And when you're configuring Phoenix as well, so quite often in IRC, people come in and go, hey, Phoenix is really slow. And go, yeah, it's not. There are two big things you need to do. You need to use the production environment, and you need to disable logging. Because if you don't do either of these things, it's gonna go slow. Disabling logging is really important, because if you don't, then you just get this giant stream of logs, and the I/O really slows down what the server can handle when it's incoming. So yeah, that's like a 6 gig GIF, by the way. 6 meg GIF even to do that. 6 gig GIF, imagine that, that's insane. So one of the easiest ways I've found to do this at scale, so if you're doing this with like 2 or 3 machines, you can probably set them up manually. If you're doing this with 45 machines, you can probably set it up manually, but and we did, but don't. So what you want to do is create like your first server and install Erlang and Tsung on it, and create an SSH key using like SSH keygen or whatever, and add it to your authorized keys. And this way, when you image it, all the clients will already have the controller's SSH key available, and it will be able to communicate. Set your own host name as well to something like Tsung controller. Set your U limit. And then you create an image, and then this way, every new server that you spawn from this image is already configured in a way that will work straight away with the Tsung controller. So yeah, that's kind of what we did and how we did it. So I guess what's next? One thing to note is that benchmarking is really expensive in terms of both time and server cost, because you imagine you've got all these servers, and you can only generate connections so fast, so you need to keep them open for a long time. So if there's any like Y Combinator dropouts or anything with like $100,000 of Amazon credits and they need to spend them somehow, then we could probably do that. So this test here was only for a single server. And when I say server as well, we need to clarify, I mean like a physical machine or a VM. I don't mean like a gen server or something. So, but what we'd like to do is multi-node as well. So we know Phoenix can handle multi-node, but we don't really know the performance impact that you're going to have, if any, from a multi-node solution. Something that more simulates real life. So we had a chat room and we had 2 million idle people, and that would be like the worst chat room ever because nothing's happening. So it would be nice to have additional, like with the sessions that you can set periodically on them, probabilities on them. It would be nice to have one that's actually sending messages and we could measure and work out what's happening with that. Benchmarking more chat rooms on a single server as well. So this is a more real life use case where you've got like, lots of chat rooms, each holding some people. So it'd be better to have that. The IP aliasing one, so it's definitely possible to get more than 60,000 connections on one machine, but we didn't. So I would like to, document how to do that so that people can do that more easily. And also automate the test. So this is a big one, automate the test for each release. So for both WebSockets and HTTP. So sometimes people raise an issue on Phoenix, and the core team will be like, okay, there's possibly a performance regression here, but we don't know because we don't run it like all the time. So we have to run these before each release, and we have to run it manually. And it'd be nice if there was a way we could just write, right, we're preparing for a release now, so let's run all the tests for WebSockets and HTTP, and then we can work out if there's any regressions. And that's it. So thanks for listening. And that was.
Thank you. We have time for a few quick questions.
Oh no.
Hey, great talk. Are you considering doing a benchmark for Phoenix presence?
So I actually forgot to mention that. There's two additional things. Phoenix presence is definitely one of the things we want to check, that it hasn't had any impact on the performance of existing Phoenix Pub Sub stuff, and also if using the presence has any impact on it. And the other one that I forgot to mention is like EXRM releases. So we want to make sure, a lot of people are going to be using EXRM for their Phoenix applications, so we really want to make sure that there's no performance impacts of using releases for that.
Hello. Did you try, this is a question, did you consider trying the benchmark on the smaller server again after you did those last changes?
So, I mean, that's a good question. We didn't because the reason we didn't is because the limits of the older test was the memory of the connections that were, we'd maxed out the memory of the server, and it's unlikely that using a pool is going to reduce the memory for the server, so I think we were maybe memory capped at that point. But yeah, we maybe should have done.
How much cash did you burn through with these tests?
How much cash? The big server that was donated to us by Rackspace costs about $1,300 a month if you were to run it, I think. Luckily, we didn't have to pay for that one. The smaller machines, I think, are probably about $2 a day. So depending on how long you leave them running for. So because we span them up and shut them down over a fairly short period of time, it didn't cost a huge amount, but it's really frustrating to have to start again each time because you don't want to keep all these servers open. So. Oh, there's a late entry.
I think we should all chip in to give it a try next time.
This guy? Yeah, that'd be a great idea.